Okay, let's make sure I don't forget any of the things I'm supposed to do. Got a recording going. And then diary. Um, okay, so um, first I want to point out a new feature that's on the site. So if you go to the menu on the left, so you might need to refresh just to make sure that you're seeing the latest version. There's a new link, questions, and what I'm going to do with that is if someone emails me a question about an assignment that I think will be of general interest, so it's like not about the student's specific answer, things like that, then I'm going to post that without names on this page. So here's a few questions from the last few days. Okay, now everybody's accounted for. So what I would suggest is, as you're working on the assignments, go ahead and check here to see if whatever question you have is already addressed, or even if not, maybe whatever is posted here might give you a start on these problems. So just to have another resource for you all to take advantage of. One of the nice things is, at least in HTML, I can put in some actual math symbols like this delta x that can't be done over email. So hopefully this is another reason to at least keep the questions coming, or at least, better yet, keep the answers coming. Because it's happening a lot where I answer someone's questions like, chances are other people in the class might like to know about this. I'm going to go back. These are just from the last few days. I'm going to go back through my emails and see if there's anything else for this assignment, like maybe tonight or something, and get that posted as well. So we have like 4 questions here already. So I expect this to be updated pretty frequently. Okay, and I want to make sure that everyone is up to speed on where things are going for the short term. I'm kind of putting the brakes on a little bit. I thought you guys would appreciate that. So with homework 2 being due now a week from today instead of today like it originally was, I've set aside today for any questions that anyone has. Okay.
I plan for it to have to get done by Thursday.
Oh, okay. Yeah, I did push it back that far, and then okay. So, all right. Well, glad that helps. So, okay. So basically, I took a couple future subtopics and tossed them out because they don't affect anything else, and I just don't like them anyway. I mean, this may be my favorite area of math, but it doesn't mean I like every single aspect of it. Far from it. Maybe I'll cover them next semester or something. And just to open up a little more room. So the Tuesday after fall break is when the midterm is set up. I am preparing a practice midterm. Like you've seen me done. Most of you have me in other classes. Seen me put up practice tests. So I'll have one ready for that too. Hopefully pretty soon, like within the next week or so. That'll cover this chapter 2 and also chapter 6. This stuff in chapter 8 maybe get into that chapter before the midterm. It will not be on the midterm. There's the final for that. Okay, so and then shortly before fall break, yes, sorry, there is class the day before fall break. That will, saw a camera move there. It's really creeping me out. I don't teach in this room very often because I don't like to, but okay. All right. Okay, well, as long as it's not affiliated with Skynet or anything. So what will happen is I want to try to see what we can do to make sure everybody's in sound footing of Chapter 2 today. Of course, you can continue to ask questions after that, like on Thursday or next Tuesday, for instance. And I will review what Dr. Chen had covered while I was away, and then transition back into Chapter 6 and keep going from there. Okay. Let's see. Um, now, so back to chapter 2. One more thing. I will try. No promises. I will try to grade the first homework this week. Now, what will happen is everything was submitted by email, so you will get it back by email. I will send you, like I'm not going to print it up, mark it up in red, and scan it, and it's all code and diaries anyway. But I'm gonna send you an email. I'm gonna answer your email in which you submitted it to me, indicating your score and where you lost points. Um, okay, so so I told you to have questions ready. So hopefully you do. This is your time, so fire away. Anybody? Yeah.
So what is the difference between f hat x and f x hat?
Okay. Well, that's actually a really good question because they happen to be equal. Um, okay. So, but it's really more of a perspective issue. So, okay. So I'll have some discussion of that in the diary here. Okay. All right, so for backward error analysis. So just to recap, what when we're doing error analysis in general, when everything is being done exactly, all right, so we have our exact value y is our output of our algorithm or function f with exact input x. Okay, so x, f, y, all exact. Okay. Our approximation is, okay, I'm going to use YH. I've done this before, but just to refresh your memory, YH will be my shorthand for Y hat that you see in the book. Okay, so that would be FH of X. So, okay, so I'll put this in a diary here. YH equals Y hat. Okay, so wherever you see an H, that refers to a hat. So the idea is, for the approximation, the input is still exact, but the algorithm is approximate. And because the algorithm is approximate, the output is also approximate. So the correct x goes in, but it's run through a f hat, which only approximates what f is doing. And then because it's only approximation, whatever you get out of it's going to be only an approximation as well. I'll give an example of that. And this actually comes from one of the explorations. I should look up which one it is. Yeah, number 5. Okay, so the true f in that problem is just cosine x. And then f hat of x is equal to the second degree Taylor polynomial that happens to be a good, decent approximation of cosine, at least near x equals 0. Now the problem, you're using pi over 4. Not quite as good an approximation there, but that's kind of a point of a problem. Okay. Now, why we do what? Now the thing is, where does x hat come into play? We haven't seen that yet, and it really comes from the difficulty that we currently have, based on what I've shown you here, the difficulty in trying to estimate error. So the goal, really, what this whole section is about, and really numerical analysis in general is all about, is estimating forward error. So now one thing I want to point out, okay, I'll call this a jargon check. Forward error, when I say forward error by itself, by default, I mean absolute forward error. And the same is true of backward error. So assume absolute error unless relative error is specified. Let me make a little more room here. Okay. Whoa, no, I said more room, not way less room. Okay. All right, because in some problems I say forward error or backward error and I don't give a qualifier on it. If there's no qualifier, assume absolute. Okay. Okay. So forward error, of course, by definition, is y hat minus y. So that would be f hat of x minus f of x. Okay. Now here's where things go badly. If we just go with that definition of our approximation as opposed to our exact value, we have no tools that we can use to try to get a handle on this difference. And that is actually why we have backward error analysis. So if I could say, in this context, it really is backward error analysis to rescue. And we make the assumption that our approximate solution, which is our approximate output, which is our approximate algorithm applied to the true input, is equal to the exact solution of a nearby problem. So the true algorithm f applied to an approximate input. Okay. Now, so this is where I finally get to the heart of your question. But I want to make sure that everybody has the whole picture here. Because I've just said this, I'm not going to call this what we had originally referred to as this. How on earth does that do us any good whatsoever? Well, it actually does us a lot of good, because if we revisit forward error, so that would be our approximation of f of xh minus f of x. So now we have a difference of two function values, but they're the same function, just at different inputs, as opposed to up here, different functions evaluated at the same input. And the reason why that's helpful is now we can use calculus. And something that you actually would have, technically it would have been taught in Cal 1, but it was probably never really talked about this way. Mean value theorem. Now, does anyone remember the mean value theorem? Okay.
Isn't it if you have 2 points on the line, there is 1 point in between?
More words needed than that. Okay.
Is the point between the 2 points on the line, and then like all three of them together make a line? Or am I thinking about the wrong value? Like on a graph.
Yeah.
Okay. Am I in the right ballpark with we're looking at graphs?
Yes.
Okay. Then it's like if you have 2 points on a graph, and the mean value would be like halfway between it or something like that, and like makes a line. Kind of.
It's probably buried in there somewhere, but okay, I think I better rescue you guys. So okay. All right. Well, first, and this might be closer to what you, Jonathan, were getting at. Rolle's theorem is good. I think you guys, when you took Cal 1, like what, forever ago? Rolle's theorem says that if f of a equals f of b, if 2 points from a function is equal, then that means that f prime is equal to 0 for some at some point c in between. Now, that is used to prove, I won't go for a proof here because this is not a calculus class, the mean value theorem says that f of b minus f of a divided by b minus a is equal to, can anyone guess? Or maybe it somewhat rings a bell?
It's the derivative of.
Yes, it's a derivative at some point c in between. So now, another way of describing this in terms of meanings of derivatives is the left side of this. Okay, well, this left side, f of b minus f of a over b minus a, does anyone remember what the meaning of that is? In terms of rates of change.
It's the slope.
Slope of what? What straight line? And besides, all lines are straight.
Tangent line?
Close. The right side is the slope of a tangent line at C. This is a slope of a different line. It's related to the tangent line. Secant line, yes. So the slope of a secant line equals slope of tangent line at a point in between. And actually, the distinction between secant line and tangent line has become very important for us at the very end of the semester when we talk about root finding methods. Now, in a Calculus 1 class, well, do you remember even seeing this in Cal 1? Maybe? Okay. And here's what they do in Cal 1, which I think is completely stupid. Is that if they'll teach you this theorem, and then they'll give you this kind of problem on it where they say, okay, here's a function f, here's some a and b, find the value of c at which this equality happens. That is the most useless problem they could possibly give you in the mean value theorem, because it's not the point of the theorem. The point of the theorem is that this exists. And so why the mean value theorem is useful in numerical analysis land, it's actually one of the most useful theorems there is it allows us to take a difference of function values, and all I'm going to do is algebraically rearrange it. This is a form in which it is useful. In other words, a difference of y values is related to difference of x values. And if I translate this into error analysis lingo, forward error, which is a difference of y values, is related to backward error. So if I return to what I have up here, forward error is now expressed this way. I can express this now using a derivative. So forward error, which is, now originally, it's this, approximate algorithm on exact input minus the exact value, but now redescribed in terms of backward error, f of xh minus f of x, is now f prime of c, some c in between, times xh minus x. It gives us a way to redescribe the error in a way that we can actually hopefully try to estimate it. So, because when it was written in this form, I couldn't really do anything with it. These are entirely different functions. Also, the function fh might be too complicated to work with because it's approximating f in some way. Whereas in this case, I could think, oh, forward error is equal to something times the backward error. Now, let's see how well you guys have been understanding what's in section 2.1. What quantity is it that's covered in this section is used to relate the forward error to the backward error? Now, in this case, it's the derivative, but what do we call that? Condition number. Excellent. So f prime of c plays the role of condition number. It's the absolute condition number. In other words, how much error in input is amplified to give error in the output. So if your function is very steep, then the small change in the input causes a very large change in the output. But it can also go the other way if the derivative behaves very differently. So if we can have some notion of derivative for whatever it is we're trying to compute, then we can get a handle on error estimation that way. And it's because that if we have a multi-step algorithm, if we have the error, a handle on the error at the end of one step, then this condition number gives an idea of how much the error could be amplified as we go to the next step, and so on. Okay. Now, well, hopefully that answers your question. All right, so that's why we go through all this, to be able to. It's all about error estimation, and this is where we differ substantially from what goes on in other math classes, where the whole point is just getting the answer, like the exact answer. We're never going to get an exact answer in this class, ever, ever, ever. Because even whatever MATLAB gives you is still an approximation. But we're trying to ballpark it, and especially when it comes to estimating error, a ballpark is enough. Because do you really care if the error in your approximation is 5 times 10 to the minus 6 versus 9 times 10 to the minus 6? Not really. But magnitude matters. I mean, if I in my research, if I see something that gives error 10 to the minus 2 when I'm expecting 10 to the minus 8, I'm going to be pretty dang disappointed. Okay. Well, let's take more questions. Yes?
In 2.1.12, do we start determining that by using Taylor's theorem, like an example of it?
Okay. Yeah. For this, you would use Taylor's theorem. So what you would do is you would replace e to the h with a Taylor expansion to try to get all this to simplify. And what you could do is, what I suggest is take this 1 and move it over to the other side, say the limit of something going to 0. And then once fill in Taylor expansion, and you'll be able to cancel a lot of things. Because what you want to do is, okay, if I flip to Taylor's theorem, okay, this remainder term is what you're after. So you'd want to get in that problem a remainder term that has some power of h. That power of h is the order of convergence. And also, since for this problem, I'll flip back to it. Since you're interested in the behavior as h is going to 0, then Taylor expand around h equals 0. Okay, more?
Like term for that.
228. Okay. Essentially, yes. Yeah. So there's two scenarios, with and without normalization. So that's the most significant part of a problem, but it's not entirely plug and chug. So if we look at the underflow level, the definition that's given, okay, right here. So you have the beta to the L part, base to the lowest exponent, and then you have M min, that's the smallest possible mantissa that you can have. And the reason why that is left vague in this definition is, it's explained down below, that the value of that depends on whether the numbers are supposed to be normalized or not. And that's why the problem asks for do this both with and without normalization. Okay, I'm going to write a little something about that in here. So this is okay. 2.2.8. Underflow level is the minimum mantissa times your base to the L, where L is the smallest allowed exponent that's given in the problem. So for the smallest mantissa, if normalized, the leading digit, D0, has to be non-zero. So the idea is you set every digit to the smallest value that it's allowed to be. And then not normalized, okay, but the thing is, your minimum mantissa still has to be overall non-zero. So the idea is you're going to set every digit as small as can be under the rules for normalization versus not normalizing. And keep in mind, for this problem, okay, you're in binary, so your digits can only be 0 or 1. So what will happen is, and keep in mind, each digit corresponds to a power of 2. So you could actually be able to come up with an actual value for the mantissa that's a power of 2, and then times beta to the L to get to the rest of your value. Yeah.
So for that one, anything that's normalized, like you can pretty much assume the smallest value would be 1.
Well, yes, it would, as a matter of fact. Okay. I didn't want to give that away, but since I'm fine with a student saying that. Yeah. And then a non-normalized one would be a lot less. Okay. Okay, of course, we've seen questions on both 2.1 and 2.2. Does anyone have any 2.1 questions? I want to prioritize those. Okay. I'm going to preemptively talk about one of these because I've gotten multiple questions on it already. Okay. Yeah, this one. So here we have two approaches to approximating a derivative. These are going to come up in a later chapter, but I thought I'd give a preview. So using this to approximate f prime of x naught, these are the error formulas that you're supposed to get. So the point of this problem is to actually come up with these using Taylor expansions. And what I did in anticipation of this problem was I presented in class a while back a similar task on taking this approximation of the second derivative. So I've incorporated that into the book. I posted this on the site earlier, but now I've filled in some more information. So you can think of this kind of as a template, if you will, for this problem, where any values of f, like x naught plus h, x naught minus h, you expand them. These are the expansions that are used for this case, and then just form this expression where f of x naught plus h and f of x naught minus h are replaced with their expansions. Simplify whatever you can, and what will pop out after the kind of manipulations that are done in here for the second derivative will be the error term. But the same thing that goes on here with the intermediate value theorem is necessary for this formula, not for this one. One important point I want to make is in the case of the second derivative, here's the error term right here. It's minus 112 h squared fourth derivative evaluated at an unknown point. And that meant I needed to perform a Taylor expansion all the way out to the fourth derivative. Now, in this case, for these guys, you're not going to be doing that. So whatever derivative appears here, that's how far you take the expansion. Okay, so essentially, follow this, and that should hopefully get you there. Yes?
So in the case of 2.112, how do we know how far to take out the expansion?
For this one. Okay. What you would do is take it out until you get to the first term that doesn't cancel. Yeah, because like in this case, if you don't go far enough, you'll get 0. And that's a good guideline in general. First term doesn't cancel, that's your error. Okay. All right. Are there any other 2.1 questions specifically?
Think of 2.1.8.
218. Okay, this one. Okay. All right, so what about that one? Or,
It seemed like when you go back to where you define well posed, it pretty much seems like the third bullet point kind of answers that question, but I wasn't sure.
oh, okay. Okay. Not entirely. But this is about the relationship that is actually brought up in discussion earlier today about how the forward error and backward error relate to one another. And yeah, that third condition for well-posedness, okay, I'll put that up. Yeah, that. We don't want to have a situation where small error in the input leads to a large error in the output. But basically, the 2.1.8 is really examining your understanding of what is forward error, what is backward error, what is the relationship between them. And keep in mind what it is that what is it really trying to get anyway. But yeah, there's actually not much to write for this one. Okay. Any other 2.1? Whoops. Okay. I want to point out something I've just added to 2.2 that I'm hoping will be helpful. Is more about like the basics of floating point number systems, the various pieces involved, and also converting numbers, things like that. And I would suggest, in trying to understand floating point number systems, starting with something you're familiar with, scientific notation, because scientific notation basically is floating point numbers in base 10. Take a look at this example right here. What we have here, if you ignore the minus, I mean, you have 1 point. Okay, this is a tacky example, but 1.2345678 that's the mantissa of this floating point number in base 10. And then the 3 here, that's the exponent. So in order to represent this exactly, we need at least 9 digits. You need at least p equals 9 significant digits available. Whereas if we didn't have that many available due to like very low storage capacity, then we would have to chop this off somewhere and settle for an approximation. What I've done here is I've added some, so I've mentioned this before, unnumbered explorations. And the reason for that is, in the final textbook that I submit in January, these will be actual explorations, but I didn't want to throw off a numbering for you guys, and I didn't want to change the assignment after I'd already given it out. So that's why these don't have numbers. I would suggest taking a look at these. I'm not suggesting do them. I mean, you can if you want, but these give some interesting facts about floating point numbers that might help you with your understanding. So, for example, when you have floating point numbers that are normalized, then the mantissa always satisfies this. The mantissa is always greater or equal to 1, and it's always strictly less than whatever base you're using. So if you're using decimal, it would be like the largest mantissa would be like 9.999 something, where how many nines depends on your precision. If it is a binary, your largest possible mantissa will be 1.111111, however many ones you're allowed to have. Like here I give some like finding the exponent. So for instance, in decimal, if you were to shift this to scientific notation, then what you would do is you would, and this is something you're accustomed to doing already, you would move a decimal point to the left, and then however many places you move it to the left, that goes into a positive exponent. And then for the second one, a number much less than 1, you'd have to move a decimal point to the right to get this in standard form, like 1.78 times 10 to the minus 6 in this case. And the thing is, unfortunately, because we're so accustomed to decimal and decimal everything, you always think of it in terms of simply moving a decimal point to the left or right to figure out what the magnitude should be. And that is kind of a disservice when you move to another base. Here are a couple examples where you're required to figure out what the exponent is in base 2. And this is where you got to think in terms of powers of your base. Like in this example, if I'm moving the decimal point to the left, what does that mean? You're dividing by 10. In this example, I'm moving decimal point to the right. That's the effect of multiplying by 10. So what you could do with this number in 998 is, and in fact, I'll go ahead and do that in MATLAB. So, okay, so if I just go ahead and divide by 2, and I'm just going to keep dividing by 2. All right, so I've done it once, twice, and I want to keep going until I have a value between 1 and 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I had to do that 9 times. So 998 is equal to this number, 1.949 times 2 to the 9th. So 9 is equal to the exponent in base 2. So if I'm representing 998 in a floating point number system, 9 will be the exponent because so that conveys the magnitude in base 2. Because 2 to the 9th is equal to 512, and that is less than 998. But 998 is less than 2 to the 10th, which is the next power of 2. That's 1024. So that's why the exponent is 9. And similarly, this number, 0.01, I would keep multiplying this by powers of 2 until I get something between 1 and 2 to figure out what the exponent should be. But that's kind of tedious to keep iteratively multiplying or dividing by powers of your base. So this next unnumbered exploration gives the formula for the exponent. And it's the you take the absolute value of your number, so you forget about the negative sign. You take the logarithm to that base of your number, and then you take the floor of that, which is the same. In other words, you're rounding down to the nearest integer, and that is your exponent. And what I'm going to do is, since this problem here, this unnumbered exploration, I've not assigned to you anyway, I'm just going to do it. So if you look at how a floating point number is represented, plus or minus m, the mantissa, times your base raised to the e power. So let's take a look at that. So x is equal to plus or minus m times, I'll use an uppercase b for base, raised to the exponent e. All right, so I can take the absolute value, so that gets rid of a plus or minus. And now I'm going to take the log, not the natural log, I misspoke there, log to base beta, or b, of the absolute value. Okay. Now, tell me you remember your properties of logs. What can I do with this expression? I have m times b to the e. So what can I do with that, with your properties of logs, to try to simplify this? I can't do it yet, though. What should I do first? What? Yeah, that the log of a product is the sum of the logs. And now, now I can do what you described in the second term. So I can take the exponent in this one and pull it down. But what is the log of the base? 1. Whatever base that is. Okay, so the log to your base of your floating point number is broken into these two parts, the log of a mantissa plus e, the exponent. So e is the integer part of the log of your number. And then the log of a mantissa, you get, whatever base, you can think of it as the decimal part. But I'm using very informal notation for which one of my colleagues would undoubtedly shoot me. Okay, so but now let's take a look at that. That means because it's the decimal part, it's greater than or equal to 0, strictly less than 1. Well, now what I'm going to do is I'm going to raise all sides. I'm going to exponentiate all sides with base b. And then I have b. Okay. So then on the left side I have beta to the 0, but that's just 1. And then I have beta to the log beta of m. Well, the exponential and log cancel each other out. So that would just be m. And then beta to the first, that's just beta. And sure enough, I have what I showed you earlier. The mantissa is always greater or equal to 1, strictly less than the base. So now we have an easy way, to, as long as you can take logs, to get the exponent of a particular number in whatever floating point system you're working with. So then what I do, here's an example of what I just added to the book that I'd suggest looking at. If I have a given number, so in this case it's e, chopped after 4 decimal places, and I want to show you how to represent that in a floating point number system in base 2, so a binary. So how do we do this kind of conversion? So if I take the log of this to get the exponent is 1. So I have to divide by 2 to get a number between 1 and 2. So this number, 1.35915, that's the number I need to get the mantissa from. And what I can do is, well, now it's between 1 and 2, as long as we're normalizing. That means my first digit is going to be 1. Now, because remember, when you're normalizing, your leading digit cannot be 0. But if it's binary, then it has to be 1. And your mantissa is between 1 and 2 anyway. So my first digit is already dictated to me by the fact that I'm normalizing. So I take this number 1.35915, I subtract off the 1, so now I have this number here, 0.35915 in decimal, and now I want to represent that in binary. So I need to express this as a sum of negative powers of 2. So the way I do that, and this is what I detail in this example, I just keep multiplying by 2. So what I do is I take my number, so this is what I want to represent, I multiply by 2. If I get something that is still less than 1, basically you multiply by 2 and you look at the digit to the left of a decimal point. Because this is binary, it's only going to be 1 or 0. Whatever the digit is to the left of a decimal point, that's your digit in your binary expansion. So I take this number, multiply by 2, it's still less than 1, so my first digit, or I should say my next digit in my mantissa is going to be 0. Then I go over here, take that number down here, multiply by 2 again. Now I get something that's greater than 1. So my next digit in my mantissa is 1, and then I subtract that off to keep going. So I have 1.4366 up here, subtract off that 1, now I have 0.4366, and then I multiply by 2 again. So you keep multiplying and subtracting, and that is what produces all the digits of your mantissa. So I suggest stepping through this on your own to understand the process. And what happens is, here's my now this is my mantissa in decimal, 1.35915. After I go through this exercise, the same number represented in binary is here. So so my leading digit of 1, that's D0, and then everything after the, well, I normally call it the decimal point, but now I guess it's the binary point now, are all my digits, D1, D2, D3, D4, that are all 0 and 1. And then I go ahead and work out what that number is. So for instance, this 1 to the left of a decimal point, that's just 1. Then I have the next digit that's non-zero is in the second place, so that's 1 over 2 squared. The next digit is 2 to the 4th, and that goes, so I have 2 to the 4th, and then 2 to the 5th, and then 2 to the 6th is skipped, and so on. So see how these binary places, instead of decimal places, are associated with negative powers of 2 over here. And what I get is, wait, something's wrong. Ah, dang it. Well, I have to fix this because I'm not supposed to get this number. I'm supposed to get this number. I multiply, and when I did this in MATLAB, I multiplied by 2. Okay. Well, I probably did this. I probably still have a command. Oh, I do. Good. Okay. All the way up to 2 to the 18th, which is, yeah, that's this number here. Okay, I need to cut that off. All right, so this expression I have right here is exactly this. So I'm going to fix the book right in front of you. Okay. Try to give fast service. Okay, so that's the number. Right now, let's compare this to the number that I want to get. 1.35915. So notice this number is pretty dang close. I could have gotten even closer if I had had more digits in my floating point system. I actually carried this out a lot further when I was first writing it, but well, what happened is I got a string of zeros after this, and it's like, okay, this is getting excruciating. So I cut it off after 20 digits of precision. in this imaginary floating point system. So p equals 20 here. So if digits d0 is 1 up to d19 for 20 digits. Okay, so all right, so I'm going to grab this. Okay. All right. So now I'll jump to that point. Okay, so here in my LaTeX file, I'll paste in what I got from MATLAB. Okay. Okay. Actually, I want to hold on to this number because I'm going to need it. And then this number is what needs to go here. Okay. All right, so I take that mantissa, multiply it by 2, and okay, so and just like when you're compiling code, like in C++, I compile this. Okay. And I'm going to put this on the side as well. Okay, so this is my ritual. Okay. Okay, voila, it's fixed. Except that looks kind of tacky, but I'll deal with that later. Okay, so and the thing is, you have a lot of numbers that we can represent exactly in decimal that we cannot in binary. But at least we can come close. And if I had done used the full IEEE double precision floating point, where I would have gone all the way out to D52, the difference would have been so slight that nobody would really care. Okay, so I recommend taking a look at this to see how numbers are converted, because then this will be useful to you when you get to this exploration, representing pi as accurately as you can in a floating point number system. And here I was a little gentler on you guys, only using 12 digits. So what you would do is you would take pi, you would figure out the magnitude like you did for e, then taking the log, and then you divide by that amount. And so now you have a number between 1 and 2, and you would go for the same exercise up to D11, multiplying by 2, taking the digit to the left of a decimal point, and so on. And what you'll find, because I already did this, you're actually going to get a rather disappointing approximation of pi. Like, you're not even going to get like 14159. I don't remember exactly what it is, but it's not that. You would need more digits in a binary in order to get that close. Because look at it this way: your last digit, if your precision p equals 12, you're going to have powers of 2 in your mantissa: 2 to the 0, 2 to the minus 1, 2 to the minus 2, up to 2 to the minus 11. Well, 2 to the minus 11. All right, so your round-off error is 2 to the minus 11, and let's see what that is. Okay, yeah, so roughly 5 times 10 to the minus 4. So you're only going to get like maybe 3 decimal places correct, something like that. So it's a little disappointing. Compared to if you have like double precision floating point, p equals 52, so then 2 to the minus 52 is this value. Okay. This is a round-off error. So that makes a big difference in how many decimal places you can get correct. Okay. We have some time. Do we have any other 2.2 questions? I especially want to handle any questions related to if you're not sure what the problem is asking. You want to get those zipped to the bud quickly. And when that happens, I always update the book in case I need to change the wording of a question, even though I promise the substance of a question will not change. Mm-hmm.
I started it.
Oh, right. Okay, this one. Wait, what?
It says use an algebraic manipulation, and like you're trying to avoid the error, so
Yeah.
like you square it to avoid messing with zeros.
Oh, no. Okay. And yeah, because so I wanted to. If a strange way in which I worded this question was intended to avoid giving too much away, as to what you would actually do. So I want to try to refresh everybody's memory, if possible, about. Okay, so this is 2.2.15 on developing an alternative quadratic formula. So what happens is, if I put up the quadratic formula we all know, okay, actually if it looks weird with all that space, I'm going to get rid of it. Okay. And what happens is, if b is positive, then of course minus b will be negative, and then plus sign is problematic, because what's happening is due to a subtraction. Like if this value is close to the absolute value of b, then b being positive will lead to a subtraction. If b is negative, then choosing the minus sign is problematic. So one of these is a potential to be a bad root due to cancellation error. And the idea is, by manipulating this, you'll make what was the unsafe root in this formula the safe root in the new formula, so that you're always going to have. So you can always use one formula or the other to make sure that both roots are computed in a reliable way, avoiding this problematic subtraction. So I'm going to show you like an example problem from probably from Cal 1, limits at infinity. Like for instance, finding a limit as x goes to infinity, I'll use two O's for infinity, of like something like square root of x plus 1 minus square root of x. And as you let x go to infinity in these terms individually, both terms individually going to infinity, you have infinity minus infinity, which is an indeterminate form. So what you can do is take this expression and multiply and divide by a certain something to get rid of this subtraction of square roots. And I don't know if you were able to find something on that earlier, because okay. Without giving anything away, does this ring a bell for anybody as to what sort of thing is done? Okay. It relates to that and what you can do with that. So again, the interest is not giving you too much away. the idea is to take advantage of what this simplifies to, in order to because look at it this way: infinity minus infinity, we don't know what that is. That's the indeterminate form. If you but infinity, if this was a plus instead, that we would know what that is. That would just be undeniably infinity. The idea is to take that subtraction and change it into an addition. So try working with that to come up with the right thing to do. If you also look at any calculus text where this also comes up, is the same algebraic technique. Finding the derivative of square root of x. So that would involve an expression like this: square root of x plus h minus square root of x divided by h. Again, you have a difference of square roots that algebraically you can't really do anything with. But again, by multiplying and dividing by the right thing, to eliminate square root signs in the numerator, you can so if you see how this is worked out in any calculus book, that's the same approach that is used in this problem to come up with an alternative quadratic formula. All right, so see if that gets you to where you want to be. Any other 2.2 in the 7 minutes we have left? Yeah.
So I have a question about 2.2.
Okay.
I was wondering how your tests were typically formatted.
Okay. Actually, I think what I can do is I may not have a practice test up yet, but I know what I'm going to base it on, so I'm going to show you from that. Keep in mind that, like everything else in numerical analysis, this is an approximation. So if I go back to same ciphers class in 2009, using the old USM color scheme. Okay. Well, actually, what we've just been talking about with that, 2.2.15, you might find along my old notes. So, okay. Because, the book is based on these notes that you see here, but there's been a lot of changes along the way. Okay, so here I'll pull up the practice exam. Actually, this would be a good example of a problem right here. Like dealing with a Taylor remainder, if we approximate this function by the second degree polynomial, Taylor polynomial, then how big can the remainder get if we limit x to a certain interval? And I'll talk about that in a moment. Let's see. Oh yeah, here this is a formula that would suffer from catastrophic cancellation. How would you rewrite it to eliminate the cancellation, which is actually that is exactly what 2.2.15 is about. Rate of convergence, like one of the last problems that you were asking about, Jesse, earlier in 2.1. Let's see. Okay, this is a good problem for a final. This is something we cover later. Nope. Oh yeah, from chapter 6, polynomial interpolation. This one too, polynomial interpolation. Okay, so there's like 5 problems right there. And in fact, I probably wouldn't have much more than that for a 75-minute test, because some of the polynomial interpolation problems in particular can take some time to work out. Okay, I want to call your attention to something involving Taylor's theorem. Okay. Well, here, you just go ahead and computing the forward and backward errors directly because you're dealing with a specific x value. But actually, take a look at what else I gave here. Okay, for Taylor's theorem. Okay, and actually there are examples here in the appendix that discusses Taylor's theorem. That we have, so I'll talk about this more later, maybe on Thursday. But if I approximate my function f by a Taylor polynomial to a certain degree, like we saw earlier in that example of cosine, I use a second degree or fourth degree polynomial, then here's our remainder. So here's our remainder term right here. So it's a higher order certain derivative of f at an unknown point, and then this factorial and this x power of x minus x naught. So then the question becomes, how big can these get? Like, if you're given x naught and you're given that x falls within a certain range, how big can this get? Also, the unknown point, c of x, that's between x and x naught. So how big can this derivative get on a given interval? So all those things put together give you an idea of how large this whole expression, because you're never going to know this exactly, but how big can it get overall, and like a ballpark, gives you an idea of how accurate your polynomial approximation can be. And this gets into finding, there's one thing I meant to talk about, but nobody asked about it today, but I've gotten asked about it by email, about finding bounds on functions. So I'll talk about that on Thursday. But at least now you can look at that, and I'll post this later about what you can expect on the midterm. All right. Okay, yeah, we're down to 1 minute, so okay.